It is important to point out that chain rule that so many of you love also applies to partial derivatives. This means that we can typically write, for example, that dz dx will be the same as having dz du dx, with z being a composite function that is z of u of x. And the Leibniz notation is still very useful for this. Same thing will go for y, where we can also write this in this form. Sometimes in physics we do use a notation just to be absolutely clear that we are looking at partial derivatives, in this case of a function that depends on x and y, and we're fixing this variable. This is what it means to have brackets and the variable here. This is what we're fixing. This is what we're varying. And in the same way, when you calculate the partial derivative in respect to y, you would write x. It goes without saying that chain rule is only valid if you're fixing x in both derivatives. There's also a very specific case of chain rule in partial derivative, that is Euler's rule, that you can see here, that is used a lot in thermodynamics, but that you don't need to know, and we won't be using it in physics 101, but I wanted to bring it up as a nice example in physics where chain rule and partial differentiation come together to give you an equation that you can then use to solve physical problems in thermodynamics, for example. Since we're talking about notation, in this case notation for chain rule and partial differentiation, it's very important to also look at the notation when we move to higher order partial derivatives. For example, second order. We've seen that for a function of just one variable, if we wanted to calculate the second order derivative, which in Newton's notation we would denote like this, we would use d squared f dx squared. This is how we would write it. We would use these like this because it only depends on one variable. Now that we've kind of crossed the line and we're looking at functions that typically we call z, which are functions of x and y, we've seen that if we want to calculate a derivative, typically we need to indicate what is the variable we're calculating the derivative against. This would be the partial derivative of f in respect to x, and this would be the partial derivative of f in respect to y. How do we write the second order derivative? It's relatively simple. We use a similar notation, but with the curve d's. We use d squared f over dx squared. This is the second partial derivative in respect to x, which is obtained when we apply d dx over f of x. And this is on itself df dx. Second order partial derivative just means doing it again. Same thing goes for y. If we want to get the second order partial derivative in respect to y, all we have to do is differentiate against y again. And I'll write it with this notation, and I've pointed out that using fy or df dy with the curled d's is exactly the same. A major difference when we look at functions of more than one dimension is that the second order derivatives can actually have a cross term. What do I mean by this? I mean that if we take things to this side of the board, let's say that you already have f of x, meaning the partial derivative of f in respect to x. What if you take this and you actually differentiate it in respect to y? You can also take f of y and differentiate it in respect to x. This implies that for partial derivatives and functions of two variables, even though we have two partial derivatives, first order, for second order, there are actually four of them. And we can write them also as f(x)(x). This is the same as differentiating twice in respect to x. We have f of y. This is the same as differentiating twice in respect to y. And then we have what we could call the cross-term partial derivatives, which I'm going to write here. Much better, now we have space. We will come back to this to define it very explicitly, but just in case this is useful for the worksheet and so that you can already start to realize the difference in notation. In this case, what we first do is we calculate it in respect to x, and then we calculate it in respect to y. The other way to write this in this notation is f(x)(y). You can probably notice a little bit of difference in the order. In this notation, this is the first thing you do, this is the second. In this notation, you start inwards and then you go out. Therefore, this is the first process, this is the second. For this second order partial derivative, we would write it as dx of df dy. And in this notation, what you're doing is first you're calculating f of y, and then you're differentiating it in respect to x. And that is why you write f of y. This is the first thing you calculate, and then you differentiate in respect to x. Again, this is the first process you do, this is the second process you do. As we shall see, typically these derivatives are the same for most functions. Not for every single function in maths and physics, but for most functions that we find, you will have this result. It's always good actually to calculate them independently, and when you find the same result, it's a very good indication that you didn't make a mistake. And if you find different results when you calculate the second order partial derivatives, I would definitely go back and try to find where the mistake is. An important question you could ask is, are these things useful for anything at all? And it turns out they are. Not only do partial derivatives, especially the first ones, allow you to see how things are changing along specific directions, and the second order derivatives will be the quantities that we're going to need to classify stationary points. Turns out that to find stationary points of curves of the form z equals f of x, y are obtained when the first order partial derivatives are both zero, so you end up with two equations. You solve them, you get stationary points, and then you calculate the second order partial derivatives to classify them in terms of being maximum, minimum, or a saddle point. But we'll get there in the next subsection.